Well, everyone, we're back. At least I hope you made it back for the third hour of Math 1 and 2, if I haven't scared you off already. So for anyone that's just jumping in, my name is Jadon Herron. I am a civil engineer with Anderson Perry & Associates at La Grande. Been working here for a little over 7 years now. Grew up in Union, Oregon. Finished out my civil engineering degree from Oregon State University and been working here ever since. So in the first couple hours, we went over a review of algebra, geometry, basic operator math, order of operations, etc. So now with the third hour, we're going to be diving into doing some practice problems. This is what I've been looking forward to the most. I think this will be a lot of fun for everyone. We can work through some problems, track units, and hopefully it's something that's applicable to what you guys do every day. And bear with me, I'm hoping that as we go through these, this is the third hour for Math 1 and 2, and then following this, I'll be presenting 2 more hours for Math 3 and 4. So if you bear with me, by the end of the day, maybe I'll be okay at presenting online here. Let's give it a shot, though. So let's jump right into sample questions here. Starting with number 1, which is the hardness in milligrams per liter of a treatment plant's well water if the hardness is 18.44 grains per gallon. So the first thing I want to do here is I want to take a look at our cheat sheet. And let's see if we can find an equation for hardness. So here we have hardness as milligrams of CaCO3 per liter. That's not quite what I'm looking for, though. Let's keep on going down and see if we have a conversion. Okay, here we go. So here we have 1 grain per US gallon is equal to 17.1 milligrams per liter. So we know we have 18.44 grains per gallon. Now let's use our conversion of, for 1 grain per US gallon, there's 17.1 milligrams per liter. So we want our grains per gallons to cancel. So we're going to put 1 grain per gallon on the bottom. And we'll put our 17.1 milligrams per liter on the top. Grains per gallon is going to cancel, and we get 18.44 times 17.1. This is going to equal 315.3 milligrams per liter. Now if we come over to our question, answer B is 315.7. The reason why we're a little bit off here from 315.3 to 315.7 is just because of the number of decimals we carried out with this conversion factor. They only gave us 3 decimals, so we're only going to be accurate to 3 decimals, or to 3 significant digits, so 315. That all looks fine. Answer is going to be B. So let's jump down to problem number 2. Find the specific yield in gallons per minute per foot if a well produces 105 gallons per minute and the drawdown for the well is 16.3 feet. So depending on the cheat sheet we have, there might be an equation for the specific yield. I didn't find one running through this cheat sheet. So what we're going to do here is we're just going to track some units. So in this case, we know we have 105 gallons per minute. And we want to know it produces 105 gallons per minute, and the drawdown for the well is 16.3 feet. Well, if we look at our answers over here, all the answers are in gallons per minute per foot. So we know that's going to have to be the yield we're looking for. Well, it asks for also the yield in gallons per minute per foot. So we have 105 gallons per minute, and we know that our drawdown was 16.3 feet. So if we divide that by 16.3 feet, we're going to get a solution that is in gallons per minute per foot. So we get 105 divided by 16.3 is equal to 6.44. Again, our units are gallons per minute per foot. Looking over here, we have B is 6.44 gallons per minute per foot. So we're right on there. All right, let's go on to number 3. If the static level in the well was 138.6 feet below ground level and the drawdown was 21.1 feet, which must have been the pumping water level in the well? So on something like this, it can be a little bit confusing. I like to draw a sketch. It really helps me clarify things. So let's just draw a schematic sketch of a well. Let's just say we got existing ground. We've got a well casing going down into the ground. And the static water level in the well was 138.6 feet below ground level. So we know this distance here was 138.6. And we know the drawdown was 21.1 feet. So they started pumping it. The well came down another 21.1 feet. Oh, excuse me there. That's supposed to be a foot marker. So, which must have been the pumping water level in the well? So we know we started at 138.6. We drew down an additional 21.1. So then we know our pumping level had to have been 138.6 feet plus our drawdown of 21.1 is going to yield 159.7 feet. Looking at our answers, we have D is 159.7 feet. Number 4. Which is the pressure in pounds per foot squared 189 feet below a lake's surface if the lake is 386 feet in depth? Okay, so we know we're 189 feet below the lake's surface. We don't really care about the 386 feet in depth because we're only looking at 189 feet. That's all we really care about. So let's take a look at our conversions to see what we have here. So we know 1 foot of water is 0.433 pounds per square inch. Well, we're looking for pounds per foot squared. We could use that one. Let's take a look at that. So we know we are 189 feet. We know that 1 foot of water is equal to 0.433 pounds per square inch. That's going to yield us 81.837 pounds per square inch. However, we want to go pounds per square foot. So, well, actually, let's do this a little differently, guys. Well, there's 2 ways we can do this. So we have 81.837 pounds per square inch. Let's write pounds per square inch a little differently here. We can do this as pounds per inch squared. Now let's convert this to pounds per foot squared. So we know that in 12 inches squared, there's 1 foot squared. So 12 inches squared is 144 inches. So if we do 81.837 times 12 squared, we're going to get an answer of 11,784.5 pounds per foot squared. Let's take a look at our question, and we know that C, 11,790 pounds per foot squared. That's our answer. That's one way to go about it. As you saw, we just tracked units all the way through. We were able to get the answer in pounds per foot squared. Now, I did an additional step. Let's step back and see if we can do this a little bit more cleaner. So, again, we know we have 189 feet below the water surface. If we use this other conversion, it's going to skip a step for us. 1 pound per square inch is equal to 2.31 feet of water. So we'll have oh, never mind. That's also in pounds per square inch. So the way we did it was the way we had to do it, because we're going to get an answer of pounds per square inch either way. I was thinking that was actually in pounds per square foot, but it's not. So let's jump on down to problem number 5. A circular clarifier has a weir length of 162 feet. Which is the weir overflow rate in gallons per day per foot if the flow is 2,330,000 gallons per day? Okay, so there's two ways we can do this. One way would be just to straight through track units. So we know that our flow is 2,330,000 gallons per day. And it's asking for our overflow rate in gallons per day per foot. So we take our flow, divide by our weir length in feet. And this is going to give us 14,382 gallons per day per foot. And that's going to line right up with answer B, 14,380. Now, alternatively, we can take a look at our cheat sheet where it outlines that the weir overflow rate is gallons per day per foot is equal to flow in gallons per day divided by weir length. We didn't even need to use our cheat sheet because we were able to just track the units right through, take our flow rate, divide by our weir length, and get our gallons per day per foot. Number 6, convert 35.1 cubic feet per second to gallons per minute. So let's see what we have for conversions. We know we have 35.1 cubic feet per second. And let's look at our conversion rates. Cubic feet per second, 1 CFS is equal to 448.8 gallons per minute. So we want our CFS to cancel, so we'll throw our 1 CFS on the bottom, put our 448.8 gallons per minute on the top. CFS cancels, and we get 35.1 times 448.8. That's going to equal 15,752.9 gallons per minute, which takes us to answer B, 15,800 gallons per minute. Number 7, convert 7.7 million gallons per day into cubic feet per second. So this is going to be really similar to what we just did. We know we have 7.7 million gallons per day. We want to go into CFS, so let's look at our cheat sheet. So 1 cubic foot per second is 0.646 million gallons per day. So we're going to put our 0.646 million gallons per day on the bottom so it cancels. And that's equal to 1 cubic foot per second. So a million gallons per day cancels million gallons per day. 7.7 divided by 0.646 is equal to 11.92 CFS, which is 12 CFS. Answer B. Let's look at number 8. How many million gallons are there in 318 acre feet? So we start with 318 acre feet. And we want to go to million gallons. Let's see if we can find a conversion here. Here we go. 1 acre foot of water is 326,000 gallons. So we want acre feet to cancel. We'll throw that on the bottom. Acre feet cancel with acre feet. And then we want to get this to million gallons though. So we have to multiply this by in a million gallons. There is 1 million gallons of water. So gallons cancel gallons, and we're left with million gallons for our units. So we do 318 times 326,000 divided by 1 million is equal to 103.67 million gallons. We look at our answers, and that would be 104 million gallons. All right, looking at number 9. Convert 68 degrees Fahrenheit into degrees Celsius. So let's take a look at our cheat sheet. So we have degrees Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8. So we have degrees Fahrenheit minus 32 divided by 1.8. And we know we have 68 degrees. So 68 minus 32 divided by 1.8. So we'll do our parentheses first, 68 minus 32. We'll take that and divide it by 1.8, and this gives us an answer of 20 degrees Celsius. So do you remember back when we were talking about algebra in the last hour of math, and I got kind of frustrated with the problem sheets we were working with when we were doing the order of operations? You see how this one is written with parentheses degree Fahrenheit minus 32 parentheses divided by 1.8. Now, this is how you typically see something written when you have two different numbers being divided by a different number. So when we follow order of operations, parentheses first, so we'll do degrees Fahrenheit minus 32 divided by 1.8. This is how I would say the correct way to show this math would be. When we were looking at the problems earlier, it was missing these parentheses here on top, and so you had to know you had to take the subtraction first and then divide by 1.8. That was a little frustrating on that last worksheet. I like how it's shown here. It's a lot more clear. So parentheses first and then division for order of operations. All right, let's take a look at number 10. Calculate 81.5% of 316. So we're going to take 316. We want 81.5% of that. So we'll take 81.5. We have to divide this by 100 because this is a percentage. So if we take 316 times 81.5, divide that by 100, we get 257.5, which is equal to C, 258. All right, let's take a look at problem number 11. If 8.25 pounds of soda ash are mixed into 45 gallons of water, which is the percent of soda ash in the slurry? So when we look at this, we have a couple things going against us. We have 8.25 pounds of soda ash, and they're mixing it into 45 gallons of water. So going back to units, first thing we gotta do is make sure that we're looking at everything in the same unit. Now, the easiest way to do this is going to be to convert the 45 gallons of water into pounds of water. So let's take a look at our conversions. And we want pounds per gallon. Let's see if we can find that here. Here we go. 1 gallon of water is 8.34 pounds of water. So we know we have 45 gallons. And we want to get to pounds of water, so we're going to put our gallons on the bottom here. So in 1 gallon, there's 8.34 pounds. Gallons are going to cancel gallons. And this equals 375.3 pounds of water. So now I want to know, what is the percent of soda ash in the slurry? So we know we have 8.25 pounds of soda ash mixed into 45 gallons, which is 375.3 pounds of water. What is the percent of soda ash in the slurry? So when we talk about the percent of soda ash in the slurry, the key word is there, in the slurry. So that's going to be the combination of soda ash and water. So we know we have 375.3 pounds of water. And we know that there are 8.25 pounds of soda ash. So this is going to give us a total slurry of 383.55 pounds. Now the problem asks for the pounds of, or the percent of soda ash in the slurry. So we know we have 8.25 pounds of soda ash and a slurry of 383.55 pounds. Now I want to get this to a percentage, so we're going to multiply by 100. And this is going to equal 2.151%. We're right there, 2.151. So that's going to round up to be C, 2.2% of soda ash in the slurry. Okay, let's take a look at number 12. Calculate the area of a circular reservoir in square feet with a diameter of 411 feet. So we can come back over to our cheat sheet here, and we can look at the area of a circle. 0.785 times our diameter squared. Here. So area is equal to 0.785 times our diameter squared, which is equal to 0.785 times 411 feet squared, which is equal to 132,600 square feet, which rounds up to be D, 133,000 square feet. Number 13, determine the circumference of a clarifier if the radius is 95 feet. So if we come back to our cheat sheet and we look at the circumference of a circle, it is equal to 3.14 times our diameter. So our circumference is equal to 3.14 times diameter, which is equal to, our radius is 95 feet, so we have to take 95 feet times that by 2 in order to get our diameter. Going back to order of operations, we'll do parentheses first, so 95 times 2 times our 3.14. And this will give us 596 feet, which is D, rounds up to be 600 feet. Number 14, determine the volume in gallons for a pipe completely full of water given the following data. Diameter is equal to 1.5 feet, length is equal to 1.09 miles. So if we come back to our cheat sheet and we look at the volume calculations, we have volume of a cylinder is equal to 0.785 diameter squared times height. And again, remember this is just the area of the pipe times the length of the pipe. So we have volume is equal to 0.785 diameter squared times height. So the first thing we have to do is get all of our units the same. So we have feet and miles. So let's convert our length of miles into feet to begin with. So we have 1.09 miles. Let's look at our conversion factors. We know 1 mile is equal to 5,280 feet. So miles on the bottom, and 1 mile, we have 5,280 feet. This is equal to then 5,755 feet. So we have miles cancel miles. So next, now we have our diameter in feet and our length in feet. So our units match. So let's calculate the volume. So volume is going to be equal to 0.785 times our diameter squared, which is 1.5 feet squared, times our length, which was 5,755 feet. This is going to give us a volume of 10,000 165.1 feet cubed. So we have feet squared and feet. Now the answer wants this in gallons though. So we come back and look at our cheat sheet. We know that 1 cubic foot of water is equal to 7.48 gallons. So we have 10,165 cubic feet of water times 1 cubic foot of water. There's 7.48 gallons. Cubic feet cancel cubic feet, and we're left with 76,035 gallons. Come back and look at our problem. Answer D, 76,000 gallons. Oh, you guys did not see that. So here we go. We have the 10,165 cubic feet times our conversion of 7.48 gallons per cubic foot. Cubic feet cancel cubic feet, and we're left with 76,035 gallons. All right, let's take a look at problem number 15. Which is the concentration of aluminum in milligrams per liter if 5 milliliters of a 0.3 grams per liter aluminum solution is added to 1,000 milliliters of deionized water? Okay, so let's start with what we know. We know we have 5 milliliters of a 0.3 grams per liter solution. So 5.0 milliliters, and we have 0.3 grams per liter of the solution. So let's get our units to match. So we start with milliliters. Oh, let's back up here. We have 5 milliliters of a 0.30 grams per liter aluminum solution added to 1,000 milliliters of deionized water. So we have the 5 milliliters. We're going to add that to 1,000 milliliters of water. So I have milliliters are going to cancel milliliters. And we know that solution was 0.3 grams per liter. So now these milliliters are going to cancel. We have 0.3 grams per liter. But now we need to convert the grams into milligrams. So in 1,000 milligrams, there's 1 gram. So now milliliters cancel milliliters, grams are going to cancel grams, and we're going to be left with milligrams per liter. So we run this through, and we get 5 milliliters added to 1,000 milliliters of water times 0.3 grams per liter times 1 gram, there's 1,000 milligrams. And this is going to equal 1.5 milligrams per liter. All right, let's jump to number 17. How many gallons are there in 28.65 acre feet? So 28.65 acre feet, this is equivalent to an area of 1 acre that has 1 foot of depth. So this is just going to be a conversion problem. So we know we have 28.65 acre feet of water. So let's convert our acres into square feet to get our units the same. So let's look at our cheat sheet. And we know 1 acre foot of water is equal to 326,000 gallons. So in 1 acre foot, there is 326,000 gallons. Acre feet cancel acre feet. And we're left with 9,335,000 gallons. Which is answer C. All right, let's take a look at problem number 19. If 7.3 pounds of polymer, assume 100%, are mixed into 35 gallons of water, determine the percentage of polymer in the slurry. So again, we have pounds of polymer and gallons of water. So let's first start by getting everything into pounds. So we have 35 gallons of water. And our conversion for water is going to be 1 gallon is equal to 8.34 pounds of water. So we have 8.34 pounds per gallon. Gallons cancel gallons, and we're left with 291.9 pounds of water. Now I want to know what the percentage of the polymer is in the slurry. So we know we have 7.3 pounds of polymer, and we add that to the slurry. So the total slurry is going to be 7.3 pounds plus our 291.9 pounds of water. We're going to multiply this by 100 for our percentage. So we'll do our order of operations. We'll do everything in the parentheses first. So we get 7.3 pounds plus 291.9 pounds. We're going to take 7.3 and divide by that, and then multiply by 100. And this is going to give us 2.45%. Because our pounds are going to cancel our pounds. And 2.45% is going to equal B, 2.4%. Number 19. Which is the percentage of removal across a settling basin if the influent is 17.1 NTU and the effluent is 1.13 NTU? So let's look at our equations. And we have removal in percent is going to be our in minus our out divided by our in times 100. So for this problem, the influent was 17 0.1 NTUs. Our effluent, our out, was 1.13 NTUs divided by our influent, 17.1 NTU, and then times 100%. So we get 17.1 minus 1.13. We'll take that and divide by 17.1 and multiply by 100. And we get 93.4%, which is equal to D. Okay, number 20. Find the detention time in hours for a clarifier that has an inner diameter of 112.2 feet and a water depth of 10.33 feet if the flow rate is 7.26 million gallons per day. So let's take a look at our cheat sheet to find out how to calculate detention time. Detention time is equal to volume divided by flow. But they even note right here that units must match. So again, like we talked about earlier, units, units, units. So first thing we have to do is calculate the volume. So let me write this down up here. So we have detention time is equal to volume over flow. So our volume, we have a clarifier that has an inner diameter of 112.2 and a water depth of 10.33. So let's go back to our volume calculations. And again, volume of a cylinder is 0.785 diameter squared times our height, which again is just the area of the circle times the height. So volume is 0.785 diameter squared times our height. So we know our volume is 0.785. Our diameter is 102.2 feet. Our height was 10.33 feet. This is going to give us a volume of 102,083.5 feet cubed. So we had feet squared and feet, so our volume is going to be in cubic feet. But now we look at our flow rate, and our flow rate is in million gallons per day. So our units don't match. We have a volume in cubic feet and a flow rate in million gallons per day. So let's go ahead and convert our cubic feet into gallons. So again, we know 1 cubic feet is 7.48 gallons. So we have 7.48 gallons divided by 1 cubic foot. For our conversion, cubic feet cancel cubic feet, and we're left with 763,584 gallons. So now we have a volume in gallons and a flow rate in million gallons per day. So we're not quite there yet. So now let's convert this 763,000 gallons into million gallons so our units match. So we have 763,584 gallons times in 1 million gallons. There is 1 million gallons of water. Gallons cancel gallons. We're left with million gallons. And this is just equal to 0.763584 million gallons. So now if we go back to our original equation of detention time is equal to volume over flow. So we know our volume, 0.763584 million gallons. Now we need to divide by our flow rate. So this is going to be equal to 7.26 million gallons per day. So I wrote this out a little bit differently. So again, our original equation was detention time is equal to volume divided by flow. So what I've done is I have my volume, 0.76 million gallons, divided by my flow of 7.26 million gallons per day. I wrote it out like this, so volume divided by flow by using multiplication sign, just so I can show you guys how we're going to be tracking our units, because our flow was in million gallons per day. So I have million gallons then per day, so the day is going to be back on top here. So million gallons cancel million gallons. This is going to get me into a detention time in days though for tracking our units. So what we're going to need to do is we're going to need to take this and multiply it by 24 hours in a day. So now days are going to cancel days. And this is going to leave us with 2.52 hours. So again, this is why it's very important to track our units all the way through the problem to make sure that when we're all done, our units match and we get an answer of 2.52 hours. Okay, let's take a look at problem number 24. A filter is 24 feet by 28 feet. Calculate the filtration rate in gallons per minute if it receives a flow of 3,250 gallons per minute. So the first thing let's do on this problem is let's go ahead and calculate the area of our filter. So the area is going to be equal to 24 feet by 28 feet. This is going to be equal to 672 square feet. Now that's our filter area. So it wants to know the filtration rate in gallons per minute if it receives a flow of 3,250 gallons per minute. They're really looking for a filtration rate in gallons per minute per square feet. So we know we're receiving 3,250 gallons per minute. We know that our filter area is 672 feet squared. So if we take our 3,250 gallons per minute flow rate divided by our filter area of 672 square feet, we get 4.8 gallons per minute per square foot. So again, this was just an exercise of tracking our units, and we get 4.8 gallons per minute per square foot. So number 25 is a similar problem. Determine the backwash rate in gallons per minute per square foot, giving the following. Our backwash flow is 13 cubic feet per second, and our filter is 25 by 18.2. So again, let's start by calculating our filter area. Our area is going to be equal to 25 feet by 18.2 feet. This is going to give us an area of 454 square feet. So it wants to know what our backwash rate is in gallons per minute per square foot. So let's go ahead and get our units, our flow rate into CFS. So we know we start with 13 cubic feet per second. Now if we look at our cheat sheet, we know that 1 cubic foot per second is 448.8 gallons per minute. So 13 cubic feet per second times 448.8 gallons per minute per CFS. So again, if you're looking at these conversion factors and you're not sure how to get from cubic feet per second to gallons per minute or vice versa, or which one you multiply by, we're just going to be tracking our units. So we're starting with 13 CFS. We know we got to have the CFS on the bottom for the CFS to cancel with CFS to be left with gallons per minute. So based on our conversion, we have 1 cubic foot per second and 448.8 gallons per minute. So that's how we know which one of these goes on top versus which one goes on bottom. So 13 CFS times 448 gallons per minute per CFS gets us 5,834 gallons per minute. So again, they want to know the backwash rate in gallons per minute per square foot. So we know that our flow rate is 5,834 gallons per minute. And our area is 454 feet squared. So then our backwash rate is going to be equal to 12.8 gallons per minute per foot squared. So again, just an exercise of tracking our units. Okay, let's take a look at problem number 26. Calculate the backwash pumping rate if a filter requires a backwash rate of 18 gallons per minute per square foot and the filter is 20 feet by 24 feet. So again, let's just start by calculating the area of our filter. Area is going to be 20 feet by 24 feet, which is equal to 480 feet squared. So we want to know what our backwash pumping rate is in gallons per minute. So we know that a backwash rate is 18 gallons per minute per square foot. So 18 gallons per minute per square foot. And we know that our filter area is 480 square feet. So feet squared and feet squared are going to cancel. Multiply this through, we're going to get 8,640 gallons per minute. So again, all we're doing here is going to be tracking our units. Let's jump down and work on our last problem here. It's going to be problem number 31. A water treatment plant has an emergency shutdown. How many water supply hours are left in a 119.8 foot diameter tank given the following data? The tank's water level is 27.6 feet. Water cannot go below 16 feet at any time to comply with fire control. And our water usage averages 483 gallons per minute. So this could be a typical problem that you guys run into. You know, you have a well go down, your controls go down, and all you're left with is the water you currently have in your tank. And so you need to know how long you can supply the town before you run out of water or you dip into your emergency fire supply. So the first thing we're going to do is we're going to calculate the volume of storage we have, or usable storage we have in our tank. And then we'll look at what our average usage is. And then we'll determine, based on that flow rate and then the volume we have stored, how long can we supply the town. So let's look at the tank. Got a big water tank sitting up on the hill. Our water level right now is 27.6 feet. And we know we cannot go below 16 feet because this is our emergency fire storage. So to calculate the volume, going back to our cheat sheet here, volume of a cylinder, 0.785 diameter squared times our height. So let's start by, that's again 0.785 times d squared is our area. So the area of our tank is 0.785 d squared. We know our diameter is 119.8 feet. So this is going to give us 94 square feet. And let's look at our usable storage. We know we're at a water level of 27.6 feet, but we cannot dip down below 16 feet for fire flow. So our usable height is going to be 27.6 feet minus 16 feet, which is equal to 11.6 feet of usable storage. Now the area in that tank was 94 square feet, so our volume of water is going to be 94 square feet times our usable storage height of 11.6 feet. This is going to equal 130,689 cubic feet. Doesn't do us a whole lot of good. We need to go ahead and convert this cubic feet into gallons. So we know we have 130,689 cubic feet. Going back to our conversions, we know that 1 cubic feet of water is 7.48 gallons. Cubic feet cancel, and this is going to give us an answer of 977,000 559 gallons. So this is our usable storage that we have in our tank. So we also know that our average water use is 483 gallons per minute. So let's take our storage of 977,559 gallons. Let's multiply that by our water use. So we have 483 gallons per minute. So I'm dividing by the 483 because again I want my gallons on bottom to cancel because it's gallons per minute. But we're looking for how many hours we have. So we know that in 60 minutes there's 1 hour. So our minutes are going to cancel our minutes. We went through and do the math. 977,000 gallons divided by 483 gallons per minute divided by 60 minutes in an hour, and we're going to get 33.7 hours. That's how long we can supply, so we better be making those phone calls and getting a new well or a new pump or new controls so we can be filling that water back up. So with that, that's going to wrap up our Math 1 and 2 review today. Hope you guys stick around. We're going to be diving into Math 3 and 4 next. Thanks, you guys.